All right. Good afternoon, everybody. I will present a joint work with Wouter Kastryk and Benjamin Smith about hash functions from superspecial genus 2 curves using Richelot isogenies. I hope these words make sense by the end of this presentation. Now, elliptic curves have been used a lot in cryptography in the past decades, isogenies lately as well, even in the 90s already, but specifically in 2006 there was a hash function based on supersingular elliptic curves. Then 5 years later, some key exchange protocol with quantum computers in mind was developed by Zhao and DeFeo. Now, last year, Takashima actually generalized this hash function to the genus 2 curve case. But then very early this year in 2019, it was discovered that there were a lot of collisions in the genus 2 hash function, which were kind of easy to spot, also to fix and avoid these collisions. And we also smoothed out a bunch of technicalities. I will not go over all of them in detail because they're very mathematical. However, all of these constructions have a graph as an underlying image that you can have in mind, which is very easy, so you can use pictures. First of all, how can we create a hash function from a graph? Let's say we have this graph, which is called the Peterson graph, and we want to hash our input 1, 1, 0. Basically, what happens is we start from a arbitrary but fixed vertex A, for example. For now, we will just simply ignore this edge going here, and we will label these other two edges 1 and 0 in some arbitrary but fixed way. Now we want to process our input or apply our hash function, which happens bit by bit. First we process the 1 and we end up in the vertex B. Now we do the same thing, but note that we have 3 outgoing edges. And now we will ignore the edge leading back. Why? Because otherwise, if we would label this 1, then hashing the empty input would be the same as hashing 1, 1, which would lead to an obvious collision, which we don't want. So obviously we continue doing this and so on. And at the end, we have an output H, which represents this vertex, whatever that may mean. Obviously, this is a very small example, which is easy to maneuver through. And we want to build something very, very large, which is easy to represent, which we will do with supersingular elliptic curves. Note as well that we were working with expander graphs. They have a lot of different technical definitions for expander graphs, but intuitively you can think of them as highly connected graphs, which don't have too many edges, which means that any random walk on the graph will lead to any vertex with uniform probability, more or less. Now, how can we create an expander graph from elliptic curves? First of all, we will fix a prime field to work over, fp squared, typically 256 bits if you want some sort of security. We will also fix a small number L, typically a small prime like 2 or 3. And the vertices will be all the supersingular elliptic curves over this field up to isomorphism. And the edges will be all the L isogenies between them. Now, what's an isogeny? This is basically some sort of very special, nice behaving map. And L means the kernel is of size L, which is all you need to know for now, really. Why are we using this? Because creating a graph like this is quite nice. The amount of vertices scales linearly with parameter p of our field size. Also, it can be proven that it has very, very good expander properties. So walking a graph is very random. And every node also has L plus 1 edges. So we can also fix the amount of outgoing edges, and we can choose that and create a lot of graphs like this. An example is like here. Obviously, 2 is a very concrete example that works for L, but 277 should probably more be like 2 to the power 277. As you can see, this is very chaotic. This is very random looking. Even 2 vertices that are close to one another, you would need to start looking to find a path between them already, sort of. But still, you can reach any vertex from any other vertex. Now, note that we have labeled these with some elements in our field F277 squared. This is basically the J invariant of our elliptic curve, which is some algebraic formula which determines an elliptic curve up to isomorphism. The only thing that I want to note here as well is, especially in the case of L equals to 2, processing one step of this, one L isogeny, is basically dominated by calculating a square root or solving a square equation over fp squared. So keep that in mind. I'll come back to that at the end of the talk. All right, now what's the security based on? Finding a pre-image in this graph boils down to the following problem. If you have two supersingular elliptic curves, we need to find an L to the power k isogeny between them, which is supposed to be hard. Even in a quantum, with a quantum computer in mind, there are no obvious ways of doing this. And finding a collision, very similarly, we need to find two distinct isogenies of maybe different degrees, could be the same degree as well, between two given curves. All right, now the general idea of generalizing this is as follows. We will fix prime L being 2. And instead of working with two isogeny, we will go to two isogenies between principally polarized superspecial abelian surfaces. I'll explain what this is. First of all, an elliptic curve. I hope everybody has seen this definition somewhere already. Basically, we have an equation, typically of degree 3 or 4. Most of the time, this is a Weierstrass form, xq plus ax plus b. But you can have 4 as well. Now, the next step is then a genus 2 curve. Instead of having a degree 3 or 4, typically we will have 5 or 6. You can have both. There are some technical subtleties between the two, but we're going to have both in mind because some formulas are really easy with 6, some are easy with 5. But there's, as long as the field has at least 5 elements, there are isomorphisms to go from 5 to 6 and vice versa. This is probably something most of you already have seen as well. This is the group law on elliptic curve. This is basically something that you will need if you want to do any sort of cryptography with elliptic curves. If you want to add 2 points on an elliptic curve, you take P and Q, you draw the line through them, you have an intersection point with the elliptic curve again, flip it about the x-axis, then you have a new point. Now we want to do this in the genus 2 case as well. However, drawing a line through this curve, through 2 points doesn't really add up to anything special. Well, it adds up to like at least 3 other points. But we're not really sure how to define a sum on that. So it's slightly different. An element in our group now will be 2 points. So we'll add this to this element, again, 2 points. And now we have 4 elements. So instead of 2 points defining a line, 4 elements define a cubic. Magically, we have 2 intersection points again. Flip them about the x-axis. And the sum of P1, P2 with Q1, Q2 is R1, R2. This is the general construction of a Jacobian in genus 2 case. You can go to higher genus, etc. as well. We don't need the formal definition, just know that there is a group law. Now we need isogeny between these objects that we're thinking about. However, if you just apply an isogeny to a domain being a Jacobian of a genus 2 curve, you can actually end up somewhere differently. So we need a slight generalization of the genus 2 curves being abelian surfaces. Instead of just working with genus 2 Jacobians, we actually need 2-dimensional algebraic varieties that are also groups. And these fall down into 2 categories. We can just have a genus 2 curve, or we can have a product of 2 elliptic curves. Intuitively, this is not too hard to imagine. You can have genus 2, or you can have some sort of degenerate case that breaks down into 2 genus 1 cases. All right, now we need them to be principally polarized. Principal polarization is an isomorphism of this form. We don't need any of that. You can just ignore this. This doesn't imply anything. It just means we have equations. Principal polarization is something that we embedded into some space. So the image you can have in mind now, the objects we work as is either an equation of this form or a product of 2 elliptic curves, which can also be seen as this form. This is very informally, but you can keep this in mind. All right, we're working with supersingular elliptic curves. What's a supersingular elliptic curve? This is one of the definitions. This is another definition, another. There are many definitions or characterizations of them. I'm just pointing this out. You don't need to know any of them. But there's a lot of ways to generalize this. Some of them don't even make sense in higher genus or higher dimension case. But most importantly, they don't all coincide. In the Takashima paper, he used the higher genus equivalent of supersingular being based on a Newton polygon. However, we noted that it would make a lot more sense to use this Hasse invariant. And in that case, they're actually called superspecial higher genus curves. Why do we want this? Because again, just as in the elliptic curve case, now we know that there's a finite amount. This time it scales cubic in our parameter P of the field size. But again, they can all be defined over fp squared. Now, why is this important? Obviously, if it would be defined over arbitrary field extensions, then doing mathematics and fp to some really high power is ridiculous. Fp is already 256 bits long. So everything being defined over fp squared is really convenient. All right, now a small example already. The objects that we're working with, the superspecial abelian surfaces over, I took f13 squared. There are 3 Jacobians of genus 2 curves, and there's one product of elliptic curves. Now again, we want to label them with some invariants. This one is rather easy. We basically have a set or multi-set, if you want, of their J invariant, which is exactly the same as the elliptic curve case. The Jacobians of the genus 2 curves are a bit different. There are a lot of invariants, but as long as the field does not have characteristic 2, there are some absolute Ihusa invariants, which is an ordered triple. Note that it's a coincidence that they are all defined over f13. Typically, it's f13 squared, so in the field extension. This is just a coincidence. Now I want two isogenies between them. As I said, a 2 isogeny is something that has kernel size 2. A 2 isogeny is something that has kernel 2 copies of Z2 with some other condition on it, mathematical, that doesn't really matter much. The most important thing is that we now have 15 outgoing isogenies every time, instead of 3 in the elliptic curve case, so our graph has a lot more edges. Also, something important to note is that if you start with a domain being a Jacobian of a genus 2 curve, it's super likely to end up again and the codomain being a Jacobian of genus 2 curve. So this happens a lot. Same with the elliptic curves, the product. This happens a lot as well, but going from a Jacobian to an elliptic curve case is very rare. We proved this with Grübner bases and some magma computations, but this part is rather trivial, but this requires some work to prove. So this is what the graph looks like then if we apply the two isogenies. Note that this is a directed graph, whereas in the elliptic curve case there were no arrows. The reason for this is in the elliptic curve case there's a nice trick that has to do with the automorphisms of the elliptic curve case, where you can canonically assign a unique arrow back for every arrow forward. Unfortunately, you cannot do that at all in the genus 2 case. The only thing you can guarantee is that there is at least one arrow back, but there could be more or less, which is a bit of a shame. But then again, we're working with hash functions, which are one way. So for us, it doesn't really matter much. It's just a technical issue that may pose problems for other applications. All right, so in general, what did we construct? An isogeny graph. We have the vertices being all these principally polarized superspecial abelian surfaces over fp squared up to isomorphism. It falls into 2 categories, and then we have all the two isogenies between them. Now, intuitively, as I said before, we have about a cubic amount of genus 2 curves, but the product of elliptic curves scales linearly p over 12. The supersingular elliptic curves scale p over 12, so the products scale with a factor of p squared. If you add the fact that the Jacobians are highly connected, so it's hard to go from one Jacobian to another, you can sort of see the interior of your graph as like the most dense amount of vertices in an order of magnitude larger than the amount of products of elliptic curves. So if you pick a random point in your graph, then it's very, very likely with overwhelming probability will be one of the genus 2 curves and not the product of elliptic curves, which is important. Why? Because in practice, we will just restrict to these Jacobians of elliptic curves. Like we have written down all the formulas. They are a lot less efficient to go from products of elliptic curves to other objects, etc. as well. But in practice, given that P is large anyway, we never encounter them, so it's a bit of a shame to try and implement it. If something has less probability of being encountered than it has of being attacked, because an attack is easier than finding a product of elliptic curves in our graph. Furthermore, if we would end in a product of elliptic curves, we would have no idea what to output. We would in a way have to like combine these into some uniform distribution, which makes the security proof harder, obviously, since we have 2 different outputs. All right, now the reason why we only use 2 isogenies is basically this. They are very easy to compute. Any higher isogenies on genus 2 are a lot less efficient. As you can see, I wrote down an equation here, which is an equation of degree 6. If it's a degree 5 equation, the math still checks out. One of the linear factors is then 0 times x plus 1. 0 times x plus 1. Now, Richelot isogeny is a 2-2 isogeny from the Jacobian of this genus 2 curve to the Jacobian of another genus 2 curve. We have 3 quadratic factors here. Let's say we want to do the 2-2 isogeny with the kernel corresponding to this ordering. Then we end up in this, the Jacobian of this genus 2 curve. The G prime 2 is basically taking the derivative of G2 with regards to x. So this is very, very simple arithmetic. And again, it can be proven that we end up with 3 quadratic or 2 quadratic and 1 linear factor at the very least. So we'll always end up on a genus 2 curve again. The only difference, the only subtlety here is this factor delta. If this delta is 0, obviously this formula doesn't work, but this is the degenerate case that you end up in product of 2 elliptic curves, so it doesn't happen anyway. It happens with probability 1 over p, so we can ignore this. The other thing is if this is not 0, then we can basically say that this is 1, so we never have to calculate or check this. Why? Because up to isomorphism, this constant factor doesn't change this curve at all. So in essence, you can, if you do some combinatorics quickly, you can see why there are 15 2-2 isogenies. Basically, it's determined by this kernel, and this is determined by the ordering of these roots. Now, obviously, if you replaced alpha 1 and alpha 2 with alpha 3 and alpha 4, you have the same kernel, you just have the same ordering. However, if you mix and match like alpha 1 with alpha 4, you have a different 2-2 isogeny. And if you write it out, you can see that there's 15 of these to be written down. So this is one step. Now, if you want to do the next step, you can do the same. You have a quadratic here, and a quadratic here. And as I said, in the elliptic curve case, one step was solving one quadratic equation. In this case, one step is solving 3 quadratic equations. Why? Because you want to split them up in linear factors again and mix and match these roots. All right, so we have 15 of these. Now, every isogeny has an isogeny back called a dual isogeny. If we take the same ordering, so if we do not mix and match any of these linear factors, and we just take this ordering, so the kernel corresponding to this, and 0, then we basically always end up in a dual isogeny. So we have to forcibly calculate the roots of our quadratic polynomials and mix and match them. Otherwise, we end up with really, really small cycles in our graph. Now, the other cycles in our graph came from something that was also easily to be spotted. If we fixed one factor or one quadratic factor and we mix and match the linear factors of the others, then this gives a 2-2 isogeny. And if we chain this, then we end up with a 4-2-2 isogeny. Now, this is an isogeny with kernel z modulo 4 plus c modulo 2 plus c modulo 2. The thing is, there are 2 other ways to make this 4-2-2 isogeny with a concatenation of 2-2 isogenies. So even after 2 steps in the Takashima hash function, you had a collision. I think about, of the 225 options, you already had 60 or something collisions just after 2 steps, which all resemble these 4-2-2 isogenies. Which means, combined with the previous slide, we cannot fix any quadratic factor. In practice, we call these the good isogeny extensions because they are good relative to the prior extension. Let's say after one step, we end up with 3 quadratic equations. We split them up into linear factors. Then the good extensions are determined by these factors. And as you can see, L1 is never combined with L2, L3 is never combined with L4, and L5 is never combined with L6. So we really need to break up these quadratic equations, mix and match the linear factors, and then we can move on. Now, concatenating this gives a 4-4 isogeny. Concatenating even further gives an 8-8 isogeny, and so on and so on. So the security is very similar to that of the elliptic curve case. Instead of having to calculate a 2 to the k isogeny between elliptic curves to find a pre-image, now we need to calculate a 2 to the k isogeny between the Jacobians of genus 2 curves. And And to find collisions, we need something very similar, where you sort of needed a subtle distinction between what a distinct isogeny is, because obviously if you apply an isogeny to something and then you apply an isogeny combined with an automorphism, then it's the same thing except up to isomorphism. It really is the same isogeny. So finding collisions in this hash function that we made boils down to finding two, in a way, distinct isogenies between the Jacobians of genus 2 curves. Now for some concluding remarks, as I said at the start, one step in the elliptic curve hash function basically means finding the roots of one quadratic polynomial. In our case, we had to do that 3 at a time. However, these could be done simultaneously. Why? Because h1, h2, h3 are independent, so we can do this in parallel, which is a big advantage compared to the elliptic curve case, where you actually had to do them sequentially. Furthermore, also the elliptic curve graph only had size linear in P, whereas the genus 2 curve graph size is cubic in P, and with any known attacks are very generic, like a Pollard row attack or something. So the fields we can work over are a lot smaller. For example, 86-bit prime versus the 256-bit prime should give 128 bits of security estimated, and obviously solving quadratic equations over a field with this prime characteristic is a lot easier. Now, some possible future research that we could do relying on this is basically the question: can we make a practical genus 2 key exchange as well with the underlying graph in our mind? Bo and Flynn already did it when they pointed out the collisions. However, one key exchange takes 5 minutes, so that's not really something practical. The main bottleneck seems to be finding an efficient 3-3 isogeny, which nobody really knows how to do yet. It's only the 2-2 isogeny that can actually be computed very quickly. And some other possible research as well, which is pointed out in our paper, is that some mathematical properties of our genus 2 curve graph are not yet proven. So for example, we are not sure about the exact expander properties of our graph, as well as some other things as well, which are too technical that I don't want to go into now. Right, that was my talk. Thank you for your attention.